Your physics teacher wants to see if you understand the universe. The Cambridge examiner, they just want to see if you can match a highly specific mark scheme. If you've ever walked out of an IGCSE physics exam feeling like an absolute genius, only to get your paper back covered in red ink, then you already know the harsh reality. Knowing the physics concepts isn't enough if you don't write exactly what the examiner wants to see. We're skipping the fluff today. We are going straight into the examiner's mindset to stop you from throwing away easy grade boundaries.
Look at this comparison. This is the exact trap so many students fall into. You get a question about a rolling ball coming to a stop, and you write, energy is lost as heat. In a middle school science class, your teacher gives you a nod of approval. But for Cambridge 0625, the examiner gives that exactly 0 marks. Nothing. The required top band answer is energy is transferred to the thermal store. It's the exact same physical event, but the first answer instantly loses marks because it uses sloppy, unscientific language. The examiner isn't just testing your general knowledge. They are stress testing your precision.
So we need a complete mindset shift right now. Ordinary revision utterly fails because it focuses on rote memorization. You're just reading the textbook over and over, hoping the equations stick. But you aren't thinking about mark scheme logic. You might know all the formulas by heart, but if you don't know the exact phrasing that forces the examiner to give you the mark, you are working way too hard for way too little reward. Our goal for this explainer is simple: minimum effort, maximum marks. We are going to sync your brain directly with the examiner's red pen.
To pull that off, you need a system. This is the ultimate 4-step framework you absolutely must apply to any energy transfer, work, or power question to lock in those top band marks. Step 1. Concept. Identify the core physics principle at play. Step 2. Evidence. Pull the specific numbers or observations directly from the question prompt. Step 3. Scientific reasoning. Logically connect your concept to that evidence. And step 4, the most important one, examiner wording. Wrap the whole thing up using the strict syllabus terminology we just talked about. Now, in just a moment, I'm going to show you the hidden examiner clue that takes a perfectly calculated efficiency answer and turns it into an instant 0. But first, you need the foundation that makes that trap completely obvious. Before you can apply that 4-step framework, we have to clear out the junk. These are the 4 most painful complaints pulled directly from the actual Cambridge examiner reports. These are the mistakes that consistently destroy student grade boundaries year after year. Missing units, rounding too early in multi-step calculations, vague explanations like the heat loss trap we looked at, and plugging the completely wrong variables into an equation just because they sort of look right. Listen, these aren't misunderstandings of physics, they are exam technique failures. Eliminate these 4 unforced errors and your score jumps instantly without learning a single new concept. Let's actually look at how this plays out on a real exam paper. Notice how the flawed calculation here loses a crucial method mark simply because the student got impatient. They calculated their intermediate values, rounded them off to 2 decimal places right there in the middle of the problem, and then used those chopped up numbers for the next step. So their final answer drifts off the acceptable mark scheme range. But look at the top band calculation. They correctly substitute all the raw values before finding the final number. They keep the full, messy, unrounded values in their calculator until the absolute very end. That is how you secure every single method mark. Okay, remember that trap I warned you about? Imagine you do everything right. You don't round early, you substitute the variables perfectly, you punch it all into the calculator and arrive at the exact, mathematically flawless number for an efficiency calculation, and the examiner still hits you with a big fat 0 for the final answer. Why? How does a perfectly calculated efficiency answer score absolutely nothing? To spot the trap, we actually have to step back and look at the absolute foundational rule of this entire topic.
And that rule is the principle of conservation of energy. You know the definition: energy cannot be created or destroyed, only transferred between stores. This isn't just a fun fact, it is a strict, unbreakable law of the universe, and more importantly, it's an unbreakable law of the Cambridge mark scheme. Examiners will ruthlessly penalize you for using terms like producing energy or losing energy. Energy doesn't just spawn out of nowhere, and it doesn't vanish into the void. It just shifts into a different store, usually the thermal store of the surroundings. Once you permanently embed this principle into your thinking, you stop making careless phrasing errors.
Which brings us right to the 0 mark reveal. Efficiency is a ratio of useful energy out divided by total energy in. Energy is measured in joules. So what happens when you divide joules by joules? The units cancel completely out. That means if you do all the math perfectly, but you tack on a J for joules at the end of your efficiency answer, it is scientifically incorrect. The examiner sees 0.75 joules and instantly marks it wrong. Efficiency has no unit. You either leave it as a pure decimal or you multiply by 100 and add a percentage sign. Adding an energy unit to a ratio is a totally fatal error.
Let's escalate things. Let's move away from these basic calculations and get into the really heavy stuff, practical data analysis. If you're doing the alternative to practical paper, or any practical-based question about a stretching spring or a simple pendulum, this is where Cambridge aggressively separates the A-star candidates from everyone else. You aren't just plugging numbers into a formula anymore. You are analyzing raw, real-world experimental data to uncover the physics story hidden inside it.
Take a really close look at this mock data table. It's tracking energy stores during a physical investigation. Let's imagine a pendulum swinging. You got columns for height, velocity, gravitational potential energy, and kinetic energy. Now watch the numbers. Notice how, as the potential energy decreases, the kinetic energy increases. But critically, look at the total energy. It remains almost totally constant, minus a tiny fraction that gets transferred to the thermal store because of air resistance. If you know how to read it, this table is screaming the principle of conservation of energy right at you.
But let's look at what a panicked student submitted after plotting this exact data. They wrote down 3 conclusions, and all 3 are massive failures. Number 1, they completely inverted their graph axes. Number 2, they wrote that kinetic energy will just increase infinitely, which totally violates the conservation law we just talked about. And number 3, their final written conclusion wasn't even supported by the numbers in the table. They just regurgitated a memorized textbook fact instead of looking at the actual evidence right in front of their eyes.
I want to try something right now. I want you to mentally pause this explainer for just a few seconds. Look at those student conclusions again. Try to predict exactly why the examiner is going to destroy this answer. What fundamental graphing rule did they forget? And how does infinite kinetic energy physically make 0 sense? Just think about it for a second. Okay, let's bring out the red pen and look at the examiner's correction. This perfectly shows how to align your reasoning with the data. First off, the independent variable, the thing the student was actively changing in the experiment, that always goes on the x-axis. That fixes the graph. Now what about the infinite kinetic energy? The examiner points right back to our golden rule, the principle of conservation of energy. Kinetic energy can only increase until all the available gravitational potential energy has been transferred. That's it. The total starting energy is a hard cap. You absolutely must ground your conclusions in the reality of the data you are given. So, let's tie this all together into a bulletproof checklist. Whenever you hit the end of an energy, work, or power calculation, you run through these 3 steps to protect your marks. Step 1. Write the correct equation out clearly before you do anything else. Step 2. Substitute your unrounded numbers directly into that equation, checking your units as you go. Step 3. Verify your significant figures, usually to 2 or 3, and then do a reasonableness check. Ask yourself, does this number make sense? If your calculated efficiency is 150%, or your swinging pendulum is somehow creating new energy out of thin air, you know instantly you need to recalculate.
We have covered some serious ground today. You know exactly how to avoid the heat loss terminology trap, you know why rounding early destroys your method marks, and you know never to put a joules unit on an efficiency answer. But here is the problem. Leaving right now means you are completely missing the second half of this puzzle. Knowing the energy concepts is great, but knowing exactly how to manipulate the tricky wording in the alternative to practical paper is where the A-star is actually won. There is a whole other layer of hidden examiner language you haven't seen yet.
We are decoding all of those mandatory practical and data analysis skills in our next session, and you absolutely need to be there for it. Subscribe to our YouTube channel, AC Exams, at acexams_IGCSE to excel in your Cambridge examinations. Because at the end of the day, acing this paper isn't just about understanding physics, it's about understanding the exact person grading your exam. Jump into the next explainer right now, and let's keep going.